Alright, Assalamu alaikum. So in this video, which is our third video in the series of lectures on electrochemistry, we'll be starting off with electrolysis of aqueous ionic compounds. Electrolysis of aqueous ionic compounds. Right. So far, in the first two videos, we covered the basics of electrochemistry. We discussed what electrolysis is and what are the requirements of electrolysis. And then in the last video, we discussed how will we actually electrolyze molten ionic compounds. We studied in the first video that electrolysis is basically breaking down an ionic compound into its constituent cations and anions by passing electricity through it. Therefore, in order to pass electricity through an ionic compound, the ionic compound must be able to conduct electricity. However, the problem is that in the solid state, the cations and the anions that make up the ionic compound are locked together in an ionic lattice by strong electrostatic forces of attraction, and therefore there are no free ions that can conduct electricity in the solid state. Therefore, for electricity to pass through an ionic compound, it must have free ions, and those free ions are achieved by either melting the ionic compound or by dissolving it in water. Now, what happens is, I'm reviewing what we studied in the last video right now. If we melt the ionic compound, we require a very high temperature for that. And why is that so? The reason is because in the solid state, the ionic compounds are held together by very strong electrostatic forces of attraction, which are very difficult to overcome and require a very high temperature. So what happens is that we need to provide that extremely high temperature in order to melt the ionic compound and achieve our free ions that will then conduct electricity. Now, since this high temperature is a requirement throughout the electrolysis, why? Because if we turn off the heating, the ionic compound will start to freeze again. It will become solid again, and it won't be able to conduct electricity anymore. Therefore, what we did was, I showed you in the previous video that if we have a molten solution sample of sodium chloride, then, in order to maintain its liquidity throughout the electrolysis reaction, we need to constantly provide it with heat, and we represent that through an arrow. Now, this makes electrolysis pretty difficult and pretty uneconomical because heating to such high temperatures and for such long periods of time is extremely difficult and expensive, obviously, especially at a large scale. Therefore, there's another way to carry out electrolysis, and that is by dissolving the ionic compounds in water. Now, obviously, there are some limitations to everything. But before we come to the electrolysis of ionic compounds using electrolysis of ionic compounds, aqueous solutions of ionic compounds, sorry, let's understand why is water referred to as a universal solvent. You would have heard this time and again that water is a universal solvent. Why? Because it dissolves almost all ionic compounds with just a few exceptions about which we studied in the video on salt formation. You can watch that video, and there we have mentioned the very few ionic compounds that do not dissolve in water. Right, coming again to this topic. So firstly, we are trying to discuss, we'll try to understand that why is water called a universal solvent? And this is basically a preamble to the electrolysis of ionic compounds. So it's not something irrelevant, it is very much relevant to your understanding of the concept. Now let's take a water molecule. Water is a covalent compound consisting of two hydrogen atoms covalently bonded to an oxygen atom. Now, because of certain properties of oxygen, what happens is, I'm not discussing those properties right now. That's part of A levels. It's one of the very first topics that you will be studying in A level chemistry. So I'll leave it for now. What happens is that oxygen has a property which causes the water molecule to have a, a slight charge about it. What happens is that this half of the water molecule, this oxygen part of the water molecule, has a slight negative charge. This weird kind of D indicates slight, partial negative charge. And since this top part has a partial negative charge, this bottom part obviously would be having a partial positive charge about it. Right. So when we add an ionic compound to water, we know that an ionic compound is made up of positively and negatively charged ions, that is, cations and anions respectively. So when an ionic compound, for example sodium chloride, is added to water, water molecules orient themselves around the ionic compound in a way that a tug of war is created between the water molecules. Let's take a look here. I am drawing a sodium chloride molecule here. And now I'll draw the orientation of water molecules. Now, since sodium is a positively charged ion, sodium ion is a positively charged ion, what happens is that we can have a water molecule here, we have a water molecule here, a water molecule here, and we can have a water molecule here, another water molecule here, and a water molecule here. So now take a look here. Sodium is positively charged. And, and water molecules orient themselves in a way that the partially negatively charged oxygen atoms of the water molecule surround it. And all these oxygen atoms will pull the sodium ion towards themselves. On the other hand, let's take a look at the chloride ion. Chloride ion is negatively charged and it is surrounded by the partially positively charged regions of the water molecule, that is the hydrogen atoms. Here we go. Now, as a result of this tug of war, what happens is that the electrostatic forces that hold the ionic compound together are eventually overcome. And therefore, in aqueous solution, the sodium chloride molecule, the sodium chloride crystal is going to give mobile sodium ions and mobile chloride ions. So let's write this down here. Alright, I'll just type this here. I hope it goes smoothly. Right. When an ionic compound is added to water, before that, let's discuss the property of water and the ionic compound as well. Ionic compounds are made of cations and anions. This gives them poles. That is one positive pole here and one negative pole. Water molecules also have partial positive and partial negative regions, as I showed in this diagram here, this small diagram. So, when an ionic compound is added to water, water molecules orient themselves around the ionic compound such that the negatively charged region, such that the partially negative region of the water molecule surrounds the cation and the partially positive region of the water molecule surrounds the anion of the ionic compound. Full stop. This creates a tug of war situation between the different water molecules. As a result, the electrostatic forces holding the ionic compound together in the solid state are overcome, and the ionic compound dissociates into its respective ions. So that's all. Let's summarize this once again. What happened was that sodium chloride was added to water molecules. The water molecules oriented themselves around the sodium chloride such that the negatively charged regions of sodium of the water molecules surrounded the cationic region and started pulling the cation towards themselves, and the positively charged regions of the water molecule surrounded the anionic region and started pulling the anionic region towards themselves. As a result of this tug of war, the electrostatic forces of attraction holding the cation and the anion together were broken, and we get dissociated sodium ions and dissociated chloride ions. Now, once this dissociation has come about, what happens is that water also dissociates into ions. And the ions that water gives are H plus and OH minus. So the second step is dissociation of water. Once the ionic compound has dissociated into its ions, water molecules also dissociate into ions, comma, giving hydrogen and hydroxide ions. So the summary of all this is that an aqueous solution of any ionic compound contains not two but four ions. So 2 ions coming from the ionic compound, and 2 ions coming from water. Therefore, if I have an aqueous solution of sodium chloride, that is NaCl, with an AQ sign here, this AQ means aqueous, that is dissolved in water. The 4 ions that I'll be having are Na plus, Cl minus from sodium chloride, and H plus, OH minus from water. Likewise, if I have aqueous copper sulfate, it is going to have 4 ions again, Cu2 plus, SO4, 2 minus, H plus, and OH minus. Now remember that acids and alkalis are also aqueous solutions, and therefore they also give 4 ions in solution. So let's take the example of sodium hydroxide. This is going to give us sodium ions, hydroxide ions, hydrogen ions, and hydroxide ions. So you can see that there's a repetition of the hydroxide ion in case of alkalis. Likewise, if we take a look at any acid, for example, sulfuric acid, H2SO4, we'll have H plus, we'll have SO4 coming from the acid molecule, and we'll have H plus and OH minus coming from the water molecules. And here we see that there is a redundance of hydrogen ions. So if we have a normal solid ionic compound, for example copper sulfate or sodium chloride or whatever, we'll have 4 distinct ions, right? However, if we have an acid or an alkali, we will have 3 distinct ions. There'll be the sources of ions will be 4, but in terms of identity there will be only 3 ions. In case of an acid, we'll have hydrogen ions coming from water and the acid both. So we can count them as 1. And in case of alkalis, we'll be getting hydroxide ions from both water and the alkali. So even though the hydroxide ions have 2 sources, they can be counted as 1. Having said that, let's now move on to let's now move forward. Now, if we talk about aqueous solutions, aqueous solutions can be dilute or they can be concentrated. A dilute solution is basically a solution where we have more water than the solute. And a concentrated solution has proportionately more solute than water. So if you're talking about a dilute solution, for example, I have a dilute solution of copper sulfate. What are the ions that I'll be having? We'll have copper ions, we'll have sulfate ions, we'll have hydrogen ions, and we'll be having hydroxide ions. If it's a dilute solution, it means that I'll be having a higher proportion of hydrogen ions as compared to copper ions, and I'll be having a higher proportion of hydroxide ions as compared to sulfate ions. Likewise, if we move on to concentrated solutions, for example, let's take a concentrated solution of calcium nitrate. So we'll have calcium ions, we'll have nitrate ions, we'll have hydrogen ions, and we'll have hydroxide ions. Since it is a concentrated solution, we'll be having proportionately more calcium ions as compared to hydroxide hydrogen ions, and proportionately more nitrate ions as compared to the hydroxide ions. Having said that, let's now move on to the electrolysis of ionic compounds when they are in aqueous state. So now we'll try to remember this, that when we are electrolyzing an aqueous solution of an ionic compound, we have to keep in account two factors. We'll write this down. Electrolysis of an aqueous solution of an ionic compound, or it will be more appropriate to say products of electrolysis. Products of electrolysis of an aqueous solution of an ionic compound are affected by two factors. Number one, the concentration of ions, and number two, the positions of the ions in the electrochemical series. Now we'll discuss both these points one by one. Let's draw an electrolytic cell containing an aqueous solution of maybe sodium chloride. Alright, now before we move forward, before we move on to the diagram, let me tell you a very important examination terminology. In CIE, in your examinations, if the examiner uses the word aqueous, just aqueous, it refers to concentrated solutions, right? So if you come across a question that says that Jane carries out an electrolysis reaction of a concentrated solution of copper sulfate, sorry, of an aqueous solution of copper sulfate, then this aqueous refers to concentrated, right? When we'll do the past paper questions, I'll show that to you as well. But now let's come to the diagram. Now since it's an aqueous solution and free ions will remain in an aqueous solution no matter what, therefore when we are electrolyzing an aqueous solution of an ionic compound, we do not need to provide heat. So I won't draw any arrows underneath. Now I am electrolyzing an aqueous solution of sodium chloride. Aqueous solution of sodium chloride in terms of CIE refers to what? It refers to a concentrated solution of sodium chloride. So what happens is that here's my electrolyte, which is NaCl, not liquid but aqueous this time, AQ. And here's my battery. Now what are the ions that will be present in this electrolyte? We'll have sodium ions, we'll have hydrogen ions, another sodium ion, another hydrogen ion. We'll be having chloride ions, we'll be having hydroxide ions, another chloride ion, another hydroxide ion. Right? So these are the four ions that will be present in an aqueous solution of any ionic compound. Two coming from the cation and two coming from the ionic compound and two coming from water. Now when current is passed through this electrolyte, what happens is that this electrode becomes the positive electrode and this electrode becomes the negative electrode. The positive electrode is going to attract the anions, that is both hydroxide ions and chloride ions will be attracted to the negative electrode. to the positive electrode. Similarly, both sodium ions and hydrogen ions will be attracted to the negative electrode, that is the cathode. So let's write this down. Right. So we observed here in this reaction that what happens is when an aqueous solution of an ionic compound is electrolyzed, all positive ions move to the cathode and all negative ions move to the anode. However, here's the catch now. Even though if we take a look here at this at our anode, both chloride ions and hydroxide ions are moving to the anode, and here we can see both sodium ions and hydrogen ions are moving to the cathode. But the thing is that only one of these and only one of these is going to be discharged. That is, we'll either have only sodium forming here or we'll only have hydrogen forming here. Likewise, we'll either be having only chlorine forming here or we'll be having oxygen forming here. Why oxygen? Because hydroxide ions have a very weird kind of equation. Four hydroxide ions reach the cathode and they produce two molecules of water, one molecule of oxygen, and four electrons. Therefore, if the hydroxide ion is discharged, it's going to produce oxygen. The taking point here is that only one of the two ions will be discharged. So what happens is that when both the cations move to the cathode and both the anions move to the anode, there's a competition between the two. That means the sodium ions will be competing with the hydrogen ions and the chloride ions will be competing with the hydroxide ions to see which of the two is discharged, whether sodium or hydrogen on the cathode or either chloride or hydroxide at the anode. So we can add this to our description that however only one of the two competing ions at either electrodes is discharged. The discharge is affected by the concentration of the ions and the electrochemical series, as I mentioned previously. So what is the electrochemical series now? We have studied the reactivity series in the previous chapters, and I also made a mention to the reactivity series in our last video on formation of salts. So you can take a look there. So electrochemical series basically is a series of ions. These are basically two series. One is a series of cations and the other is a series of anions. Uh, if we take a look at the series of four cations, we know the series. It is please, send, cats, monkeys, and zebras in to a large hired cages make sure padlocked good. This is the reactivity series of metals. And we know that metals always produce cations. So if we convert these to ions, we'll have K plus, Na plus, Ca2 plus, Mg2 plus, Al2 plus, Zn2, Al3 plus, sorry, Zn2 plus, Fe2 plus or 3 plus, then Sn2 plus, Pb2 plus, H plus, Cu2 plus, Hg plus or 2 plus, Ag plus, Au plus, Pt plus. Right. So this is our series of cations. Now, when we are referring to metals only, na, this series is called the reactivity series. However, when we come to ions, ions are chemicals and they have electrical charges. Therefore, this series is referred to as the electrochemical series. And what happens is that as we go down the series, the ions become easier to discharge. That means that if, let's say, I have a competition between equal amounts of maybe magnesium and tin, then tin will be discharged. Why? Because it's lower in the reactive in the electrochemical series and it's easier to discharge what's lower in the electrochemical series as compared to what's higher up. Similarly, if I have a competition between equal amounts of hydrogen ions and let's say zinc ions, then hydrogen ions will be discharged and not zinc ions. Why? Because hydrogen ions are lower in the electrochemical series and hence they are easier to discharge. This is the electrochemical series for cations. We have a similar electrochemical series for anions as well. And there's a mnemonic, it's a pretty weird mnemonic to remember it, but it helps me a lot. So the mnemonic goes this way. Faisal Sabzwari never cooks biryani in oil. Faisal Sabzwari is a politician. No offense to Faisal Sabzwari, this is just a mnemonic to help us remember stuff. So F stands for fluoride, S stands for sulfate, N stands for nitrate, C stands for chloride, V stands for bromide, I is iodide, and OH is hydroxide. So if, let's say, we have a competition between equal amounts of sulfate and hydroxide, then obviously hydroxide will be discharged. Why? Because it's lower in the electrochemical series and whatever comes lower in the electrochemical series is easier to discharge. Likewise, if I have a competition between equal amounts of chloride and hydroxide, again hydroxide will be discharged. Why? Because it is lower in the electrochemical series and what's lower in the electrochemical series is easier to discharge. However, there's an other factor that affects which of the ions is discharged, and that is concentration. Now remember, concentration can have an effect on the discharge to only a certain extent. If I have a concentrated solution of sodium chloride, for example, then what moves to the anode? Chloride and hydroxide. So that's what moves to the cathode, and we know that chloride is the more concentrated ion as compared to hydroxide. Therefore, what happens is that chloride, owing to its higher concentration, will be discharged even though it's higher up in the reactivity series as compared to hydroxide ions. Now, what's the criteria for deciding discharge? So this is a very golden rule, and you should remember this rule always. So the rule is the concentrated ion will be discharged. But that's not all. There are conditions. The concentrated ion will be discharged if the distance between the competing ions in the electrochemical series is 3 or less than 3. If the gap between the competing ions is more than 3, then the ion lower in the electrochemical series will be discharged. So this is a golden rule, and it's this rule which will be used throughout the electrolysis of aqueous solutions. This rule. So now let's apply this rule to electrolysis of aqueous sodium chloride, that is concentrated sodium chloride. So what happens at the cathode? Sodium ions and hydrogen ions move to the cathode. And what happens at the anode? Chloride ions and hydroxide ions move to the anode. Now, since it's a concentrated solution, we have a higher proportion of sodium ions and a higher proportion of chloride ions as compared to hydrogen ions and hydroxide ions respectively. So what happens is that according to this rule, the concentrated ion will be discharged if the distance between the competing ions in the electrochemical series is 3 or less than 3. So now let's take a look at the ions that are moving to the cathode. Sodium ions and hydrogen ions move to the cathode. So according to this rule, sodium ions should be discharged. But let's take a look at the electrochemical series. Here is sodium and here is hydrogen, and this is a very big gap. Now let's take a look at the second part of the rule. If the gap between the competing ions is more than 3, then the lower ion in the electrochemical series will be discharged. Since the gap between sodium ions and hydroxide ions is much greater than 3, it is the hydrogen ions that will be discharged, despite the fact that sodium ions are more concentrated. The reason is that sodium ions, despite their high concentration, cannot now do anything about the discharge. Why? Because there is a huge gap. Let's take a look at the anode. The concentrated ion should be discharged if the gap between the competing ions is 3 or less than 3. So now let's move back to the electrochemical series. So here we see, here is chlorine, which is the concentrated ion, and here is hydroxide. What's the gap between them? It is exactly 3 ions. Therefore, chloride ions will be discharged. Let's take another example. Let's do the electrolysis of dilute copper sulfate. Dilute copper sulfate. So when we are electrolyzing dilute copper sulfate, what do we have at the cathode? At the cathode we have copper ions and we have hydrogen ions. And at the anode we have the sulfate ions and we have the hydroxide ions. Since it's a dilute solution, we have higher proportions of hydrogen ions and hydroxide ions as compared to the copper ions and the sulfate ions. Now, according to the rule, the concentrated ion should be discharged if the gap between the competing ions is 3 or less than 3. So now let's take a look at the electrochemical series for cations. Here is hydrogen and here is copper. The concentrated ion is hydrogen and the gap between the competing ions is just 1. Therefore, hydrogen ions will be discharged. Now let's move to the anode. The hydroxide ion is the more concentrated ion, and if the gap between the sulfate ions and the hydroxide ions is 3 or less than 3, then hydroxide ions should be discharged. So let's take a look. Here is sulfate and here is hydroxide. Hydroxide is much lower than sulfate. The gap is much more than 3. Therefore, no matter what the concentration is, hydroxide will be discharged. Let's take another example. Let's see what happens if we have concentrated uh, um, CuSO4. Again, at the cathode we have Cu2 plus and H plus. At the anode we have SO2 4 minus, SO4 2 minus and OH minus. Now we can see that since it's a concentrated solution, we have higher proportions of copper and sulfate ions as compared to hydrogen and hydroxide ions respectively. So now according to the rule, the concentrated ion should be discharged if the gap between the competing ions is 3 or less than 3. Let's go to the electrochemical series for cations. So we see that here is copper and the gap between the competing ions is just 1. Therefore, copper will be discharged. Now let's move to the anodic side. At the anode, what do we have? We have the hydroxide ions and the sulfate ions competing with each other. So if the gap between the competing ions is 3 or less than 3, then the sulfate ions should be discharged. But we can see that the gap between sulfate and hydroxide is too large. Therefore, the lower ion in the electrochemical series is discharged. And therefore, despite the high concentration, the ion that will be discharged is the hydroxide ion. Right. I guess the video has become a bit long. We will continue with the electrolysis of aqueous ionic compounds in the next video, where we'll be covering the equations and observations. It'll be a short video, inshallah, and we'll find up with electrolysis of aqueous compounds. With that, until the next video, Assalamu alaikum warahmatullahi wabarakatuh. And